Okay, let's continue on with the next lesson in this unit from section 8.3. Remember this unit is rational functions. In this lesson, though, we will have the goal of graphing rational functions and identifying the x-intercepts, vertical asymptotes, also horizontal asymptotes, and we'll discuss some domain and range as well. Please have these goals or targets in your notes for tomorrow. Okay, before we continue on, let's review what the meaning of degree is. We're going to need degree, the concept of degree to answer or help us narrow down some key concepts in this section. So let's review what degree is. First of all, degree is the highest power of an equation. Okay? So if we look at an equation, for instance, x squared plus 3x minus 4, the degree of this one is 2 because the highest power is 2. F of x equals 2/3 x plus 10. The degree of that one is 1, which for the x, the first part is the highest. The degrees down here, well, even though it's out of order, the degree of that is 4. It's the highest power. And I don't see an x here, so the degree is 0. Constant function. Okay, so remember back a few chapters ago, back in semester 1, we talked about degree functions, known as chapter 5. Summing up rational function graphs, this chart might help narrow things down for you and help give you a quick reference guide as we go through to graph these and describe these functions. So if you have a rational function, p of x divided by q of x, where p of x and q of x are polynomials, and q of x is not a constant function. Q of x is a constant polynomial, then it's not really a rational function. The x-intercepts are when the numerator equals 0. The numerator is p of x equals 0. And the vertical asymptotes are when the denominator, or q of x, equals 0. So those are going to be two things that are going to hold true no matter what. Horizontal asymptotes, those are going to change depending upon the degrees of the numerator and the denominator and how they relate to each other. So if we look at this left column of this table as the degrees of each of these, that's what we're going to compare. So if the degree of the numerator, p of x, is smaller than the degree of the denominator, q of x, the horizontal asymptote is y equals 0. So that's the horizontal imaginary fence line, right? That's what asymptote is, that line that divides a graph where the graph does not touch or cross that line. P of x equals q of x, so the degrees are the same. The horizontal asymptote is y equals a over c. We saw that one the other day when we had two linear functions for the numerator and denominator. It was a over c, so that carries true whether they're linear or not. And if the p of x is greater than q of x, the degree of p of x is greater than q of x rather, there is no horizontal asymptote at all. So please have this little summation of rational functions in your notes. It's going to help you out as you go problem. Okay, so let's use that chart on the previous page to help us answer some questions and to graph this polynomial. We're also going to use the graphing calculator. So what happens when the degree of the numerator equals the degree of the denominator? Well, a few things we can look at. One, the vertical asymptote is when the denominator equals 0. So let's start there. Vertical asymptote, x squared minus 1 equals 0. Well, to solve that, we would have x squared equals 1. We would square root both sides, and we get x equals 1 and negative 1. So our vertical asymptotes for this graph are x equals negative 1 and x equals positive 1. Horizontal asymptote. Well, back in the notes, we saw that when the denominators are the same, as we have squared over squared terms, then it's a over c. The a value for this is 3. The c value is 1. So horizontal asymptote is y equals 3 divided by 1, or y equals 3. So 1, 2, 3. There's my horizontal asymptote. The x-intercepts are when the numerator equals 0. Our numerator is 3x squared. Solving that, we divide by 3. We get x squared equals 0. We square root both sides. X is 0 because there's no such thing as a positive or negative 0. So that value is actually on the graph. I'm going to use a green dot for that. That's going to be what we label the graphs with. So we have all those things labeled. Let's actually graph it on our calculator. That might help us with our domain. Helps me anyway. I go to y equals, and I'm going to type in alpha y equals to get my fraction. You can also just put the numerator in parentheses, then divide it by the denominator in separate parentheses. That would work as well. X squared minus 1. So we're going to graph. Let me put it on the large screen here so we can see that. And if we look, I think this graph matches up quite nicely to what we have here. Okay? We can see the graphs are very similar, and all I'm going to do is have a rough sketch of each. Pretty looks like we have a parabola type shape on this middle part, and the two looks like that one. And the left and the right pieces here, they kind of fit inside the upper right and the upper left little area. So if you imagine that like fence for a neighborhood dividing a subdivision, it's kind of like they have like their own little space. That's what the graph looks like. Let's look at domain. Domain is restrictions on the x. Are there any restrictions we have for the x coordinate? Well, if there's anything that restricts the x coordinate would make a vertical asymptote. So the restrictions on our domain are where the vertical asymptotes are. So I would say all real numbers where x does not equal 1 or x does not equal -1. Okay? You can also all real numbers if you use this r. The double line through it, that also means all real numbers. Okay, but so that's our domain. We can plug in anything we want. We're going to get a y value out, except at 1 and -1. If we go to our table also shows that because it gives us an error at 1 and -1, but it will give us outputs for other values. Okay? Okay, let's look at a problem where the degree of the numerator is higher than, or greater than the degree of the denominator. We see of an x squared minus 2x minus 3 over x minus 4. Squared is bigger than x to the first power. So we go to our chart to help us answer these questions. First of all, the vertical asymptote is always the same. It's when the denominator equals 0. Our denominator is x minus 4. X minus 4 equals 0. That's an easy one. X equals 4. So we have one vertical asymptote and x equals 4. 1, 2, 3, 4. Put a dotted line. Our x-intercepts are when the numerator equals 0. The numerator is x squared minus 2x minus 3. That's 2x minus 3. That equals 0. Well, we have two ways, well, more than two ways, but the two main ways we use for solving this type of equation is either the quadratic formula or factoring. You could also graph that one on its own, x squared minus 2x minus 3, and see where it crosses the x-axis to find the zeros, intercepts, roots, whatever you like to call them. Or we could do completely square. So there's many methods we can do. Let's do bottoms up if we can. We'll do some practice because we'll be using that method coming up in the next few sections. A times C, what adds to make B? Our A and our C are 1 times -3. My B is -2. What multiplies to make a -3 and adds to make -2? Well, -3 and 1 will do the trick. So this will factor to x minus 3 and x plus 1. Bottoms up, you divide by A. A is 1 in this case. So it's not going to, 3 divided by 1 is 3, 1 divided by 1 is 1. So this is factored. Obviously, FOIL it back out to make sure you're right. Do that for you. x minus 3 equals 0, or you can also graph x minus 3 times x plus 1 in y1 and in y2 of x squared minus 2x minus 3, and make sure you get the same output values, the same graph. But it should all work out. We have these two factors. We set them equal to 0. We get x equals 3 and x equals negative 1. So those are my x-intercepts. X equals positive 3, x equals negative 1. And the domain, well, we'll look at the domain in a minute here. Do we have any horizontal asymptotes? So, horizontal asymptotes. Well, horizontal asymptotes, if we look back at our chart, one second here. Horizontal asymptotes, when the degree of the numerator is greater than the degree of the denominator, we can see in that bottom part of the chart, it means there's no horizontal asymptote. So that's why there's not one label on this slide. So that's why we don't have it, no horizontal asymptote for this one. So if it asks us for a horizontal asymptote, because on the test it might do that, horizontal asymptote, we would say none. Okay, so what is our domain then? Well, I'm going to try graphing this on my graphing calculator to help me with the domain. So y equals, and I'm just going to go up here and I'm going to clear out the numerator, and I'm going to type in the new numerator that I need, x squared minus 2x minus 3. And in the bottom, I just have x, oops, can't do that, x minus 4, clear that out, x minus 4, and I'm going to graph. Now, this looks good on the left side, but remember we had an asymptote line here at 4. And I can see in my table that on this page that at 4 there's an error message, but how come there's nothing to the right? Well, let's go to my table and explore that. It looks like when we go to the right of the asymptote line at x equals 5, we jump all the way up to 12. I can't see that in the window that I have. My window ends at 10. So I'm going to go to window and I'm going to make my y value, my y max, I want to go up, and we've done this before. We're going to manipulate so that the y max is now 20 on my graphing calculator. Let's see what happens now. Now we see the graph. Slide that out. And that looks like it lines up with our asymptote line quite well. Okay, we go up, we go through the intersection points of -1 and +3. And we have two graphs that approach that x equals 4 line that do not cross them. So I'm just going to approximate this as long as I got these critical points labeled, as long as I approach my asymptote line but do not cross it. And it looks like at x equals 5, we go up to 12, so we're going to go by 2. 2, 4, 6, 8, 10, and here is 12, just above it. So 5, 12 is a low point. And the graph kind of comes down, and it's almost like a check mark type looking thing, a reverse check mark. But that's what it looks like. We approximated it. If I really want to get more values, I can go back to my table and get more values, but that's good enough for me. Now let's go back. I just realized I skipped over the first example, but that's okay. It doesn't matter what order we're doing them. Let's look at one where the degree in the numerator is less than the degree in the denominator. Okay? Vertical asymptotes. That's usually where I like to start. Vertical asymptotes are still where the denominator equals 0. Denominator is x squared plus 2. So when we solve that equation, we get x squared equals -2. When I square root both sides, I'm going to get x equals plus or minus I square roots of 2. We'll square that negative number. I can't graph imaginary numbers on the xy coordinate plane. So if I get imaginary asymptotes, then my answer is I have no asymptotes, or there are none. X-intercepts and horizontal asymptotes, we'll do those as well. Horizontal asymptotes, so if we go to that chart that we looked at, let's put back On the chart, when the numerator is greater or less than the denominator in terms of degree, then the horizontal asymptote is automatically y equals 0. So, for this one, it's y equals 0. X-intercepts are where the numerator equals 0. Well, the numerator is 4. 4 equals 0 does not make sense. So that would mean that there are no or none x-intercepts. Which makes sense. If the horizontal asymptote is y equals 0, there can't be any x-intercepts. It can't happen. If the asymptote line is the x-axis, then the graph can't also at the same time cross the x-axis. Those are contradictory of one another. Only one of those two things can happen. Domain and range. Once again, we're going to look at the graphing calculator to try and get our domain. And this time we're going to do the range just for fun. So I'm going to go up to my numerator. I'm going to clear this out. Type in 4 divided by x. Let's clear this out. X squared plus 2. Let's graph it. Let's see what we get. This is a bigger scale that I got, but it looks like that's going to line up with what we have here. I forgot to label our horizontal asymptote, but that is y equals 0 right there. Our graph is all above that line. It looks like it goes up to a certain point and comes back down. Let's see if we can find that in our table. Oops, that second trace. On our table values, it looks like 0 is a high point, 0, 2. So we go up as high as 2 and down almost to 0. So we go something like this. It's like a little mini hill in the distance. So, domain. Is there any values we can't plug in? Remember, that's tied to our x-intercepts. If I have no x-intercepts, and I have no restrictions on our domain, so our domain is all real numbers. I hate to write that right off when you're dealing with rational functions. And that's because the zeros of the denominator are imaginary. Range. The range, what are the y values? Where are they restricted to? Well, our y values never go below 0. They actually never touch 0. So they are greater than 0. But they're also smaller than or equal to 2, because 2 is the highest we go. So our range are all real numbers between 0 and 2. So, looks like we've completed this lesson. I think we've been able to graph rational functions, making rough sketches by hand, but mostly using our graphing calculator. We've identified x-intercepts, vertical asymptotes, horizontal asymptotes, as well as some domain and a little bit of range as well. So those are our targets. I think we hit them quite well. We'll see how we do in class tomorrow with the assignment.